Hello, my amazing students. This is Mrs. A, and we are back here to finish 6.1 and 6.2, which is one video that I'm doing together to include all of the normal probability distribution. So we're starting back with the triglyceride problem. All right, so here we have more about how to use technology to do these problems. Triglycerides are a type of fat in the bloodstream. The mean triglyceride level in the United States is 134 milligrams per deciliter. Assume the triglyceride level of the population in the United States are normally distributed with a standard deviation of 35 milligrams per deciliter. You randomly select a person from the United States. What is the probability that the person's triglyceride level is less than 80? Use a technology tool to find the probability. All right, so we're going to rotate our slide here. And we have here the three different types that they're showing. Must specify mean and standard deviation of the population and the x values that determine the interval. In ours, the x value is less than 80. So what we're going to do is we're not going to worry about Minitab or Excel. We're going to go straight over here to our TI 8384 calculator, and we're going to use normal CDF, because remember the CDF is the cumulative distributive function, and that's the one we want because we want everything to the left of the 80, not just 80, but everything to the left of 80. So we're going to start this negative 10,000 tells us that we are way unreasonably far to the left. In other words, there's nothing that could be behind it to the left. So we're starting way to the left. We're going up to 80, and then this is our mean, and this is our standard deviation of the entire population. And when we put all of that into our calculator, we're going to get 0.06, which means that we have a 6% chance of randomly selecting a person that has less than 80 triglyceride level when the population mean is 134 and the standard deviation is 35. Okay, so I'm going to try to do this for you on the calculator. I'm going to go to second in distribution here, and then I'm going to, first I'm going to turn on my calculator. That always helps. I'm going to go to second and then this distribute button here, and I'm going to go to normal CDF right there, and I'm going to hit enter. So then I'm going to enter in the negative 10,000 to say I'm coming from way to the left. I'm going to enter in my 80, which was we wanted a less than 80 triglyceride. I'm going to enter in the 134, which was the mean of the population, and the 35, which was the given standard deviation of the population. I'm going to close my parenthesis. I'm going to hit enter, and I get the same 0.0614 that they did on their calculator. So that's how you're going to use your calculator to get those probabilities. It's pretty cool. All right, so in the last section we were talking about how do you find the probability. Now we're talking about how do we find the value. Last time we were given a value of 80, and we had to find the probability that a random person would be less than 80 triglycerides. But now we're backing this up a little bit, and this little illustration is showing that. Okay, so earlier we were given a normally distributed random variable x, and we were asked to find the probability. So they're saying here's the x, we went to a z-score, then we went to the probability, but now we're going backwards. So in this section we will be given a probability, and we will be asked to find the random value, the value of the random variable x. So we're going backwards on that whole procedure now. So this section presents methods for working with normal distributions that are not standard. That is, the mean is not 0 and the standard deviation is not 1 or both. So we're doing a normal distribution, not a standard normal distribution at this point in time. And we're going to have to turn it into the standardize with the z-scores. So the key is that we can use a simple conversion that allows us to standardize any normal distribution so that the same methods of the previous section can be used. So we did that when we were going this direction, and now we're going to do it the other direction as well. Okay, so here is our formula. Now the z-score is the random variable x that we're talking about minus the mean divided by the standard deviation, and we're rounding the z-scores to 2 decimal places, so we've been using that before. The formula allows us to standardize any normal distribution so that x values can be transformed to z-scores. Okay, so here are helpful hints for those cases in which the area or probability or percentage, they're the same thing. The area under the curve, the probability, and the percentage are all the same thing. Okay, so when we know those, and we must find the relevant value. So that's the value of the random variable x. Graphs are extremely helpful in using, visualizing, understanding, and successfully working. So draw a graph. It'll make it clear to you what you're trying to do. Don't confuse the z-scores with the areas. The z-scores, when you're talking about your table, I'm going to show you this. So here's your table in the back of the book. These are your z-scores right here. Okay, so if I wanted negative 2.45, I'd go negative 2.4 there, and then I would come up here underneath the 0.05, and I'd come down, and I would meet those two across like that. Okay, now this area, this right here is the area under the curve. This is also the probability or the percentage. So basically you've got out here on the sides is the z-score. And inside the table is the area under the curve. Okay, so here we have a decent picture here. The z-score is how many standard deviations we are from the mean here. And then the number that we're seeing here in the middle of the table is that area underneath the curve. Okay, so they have the negative z-score. The area here is less than 0, is less than it would be. 0.5 would be exactly at the 0 mark, because remember 0 on a standard normal is the mean. And so halfway through the curve would be 0.5 or 0.50. So on the left-hand side, we're always going to have an area that is less than 0.5, which you can see as you look through the table. All of the areas here on the left, it's hard to see this, my camera's not very good, but you've got one of these in the back of your table. All of these on the left-hand side are less than 0.5. But over here, you see the little figure up here on the positive z-score, we are to the right of the halfway point. So everything on this side of the table should be greater than 0.5. And this first one is 0.5. And then from there, they get bigger all the way down until we get so very close to 1. Okay, so again, this inside is the area under the curve, which is also your probability. And this on the side is your z-score. So hopefully that helps. So then back here to this slide, it says don't confuse z-scores and areas. The z-scores are distances along the horizontal scale, but areas are regions under the normal curve. So the z-scores are in the left column and across the top row, but the areas are found in the body of the table. So the next part says, choose the correct right-left side of the graph. Okay, so a value separating the top 10% from the others will be located on the right-hand side of the graph, but a value separating the bottom 10% will be located on the left-hand side of the graph. So you have to think about what your graph should look like, and hopefully your graph will help you in figuring out what you're doing as far as the area under the curve. So a z-score must be negative whenever it is located on the left half of the normal distribution, and The areas or probabilities are always in between 0 and 1, and they are never negative. So areas can't be negative, but a z-score, if it's to the left of the 0, will be negative. Okay, so sketch a normal distribution curve, enter the given probability or percentage in the appropriate region on the graph, and identify the x values being sought. Okay, so how do we do that? If we're using technology, refer to the instructions at the end of this section. If using table A2, refer to the body to find the area to the left of x, and then identify the z-score corresponding to that area. Then we would have to go from z-score to x value to find the value that it goes with. So we're going to do some examples here in just a minute. If you know the z-score and must convert to the equivalent x value, use the conversion formula by entering the values for mean, standard deviation, and the z-score found in step 2, and then solve for x. Okay, now this is nothing but your z-score formula turned around. All right, so this is our z-score formula, and z is equal to the x value, which is your random variable x value, minus the mean over the standard deviation. And we're going to turn this around algebraically into what you see on the screen over there. So what we're going to do is try to get x by itself. So I'm going to multiply both sides of the equation by my little baby sigma here. So I'm going to get z sigma equals x minus mu. Okay, so then I'm trying to get x by itself, so I'm just going to add the mean to both sides. So I'm going to get mu plus z sigma equals x. Okay, so mu plus z sigma is x, or x is mu plus z sigma. So this is a product here multiplied together. And now look at the screen after you've seen this, because that's exactly how they got it. Okay, so look, we've got x is mu plus sigma z, and they have x is equal to mu plus sigma z. So all they're doing is taking the z formula and turning it around and solving for x. So then it says refer to the sketch of the curve to verify that the solution makes sense in the context of the graph and in the context of the problem. So it says here, draw a bell-shaped curve and identify the region under the curve that corresponds to the given probability. If that region is not a cumulative region from the left, work instead with a known region that is a cumulative region from the left. So in other words, we're going to work with something that is known, and I'll show you what we're doing with that there. So it says use technology or table A2 to find the z-score. And then what are we going to do? We're going to go from the probability that's inside the table to the z-score across the top. And then we're going to go from the z-score to the x-score using the formula we just talked to. Okay. With the table, we're going to use the cumulative area from the left, locate the closest probability in the body of the table, and identify the corresponding z-score. So let's see how this works. Find the z-score that corresponds to a cumulative area of 0.3632. Now, we're going to do this with the table first. All right, now 0.3632 is less than 0.5, so I am on the left-hand side of my page, and I am looking 0.36, trying to find it here, 0.3632. And 35, 34, 36 is going to be right there. Okay, so I finally located it. And that's on the left-hand side of the table because it is less than 0.5. So now I'm going to keep my finger there and I'm going to zoom out. Okay, and here 3632 is right there. And now let's go back. I'm trying to zoom out here. All right, so you see my table. I'm on the left-hand side, negative z-scores. And now we're going to go to the left where my finger is going to follow that little yellow line. And it's negative 0.3. And then I'm going to go up all along here and it's going to go up to 0.05. So 5 is the last digit, and here's my number again, 0.3632. Go over here, negative 0.3, and so the top one was 5, so negative 0.35 should be our answer. All right, so let's go to the next page, and they're showing you the area. Remember, they said graph it first so you know what's going on. The cumulative area is always going to be in the table. It's always going to be what's happening to the left of the value. So we're looking for the area to the left as being 0.3632. We found it in the table. It was on the left-hand side of the book because it's below 0.5. And then here's a different table that they're showing you in here that makes it a little bit easier. And they will actually go and find the value for you, 0.3632. And then they'll go to the left and up, and they'll get negative 0.35. And so that is the z-score that goes with what they're asking us here. The values at the beginning of the corresponding row and the top of the row give the z-score. Okay, so now it says find the z-score that has 10.75% of the distribution's area to its right. Okay, well, if 10.75% of the distribution's area is to the right, that's 0.1075 or 0.1075. Remember, when we take a percentage of something, we're going to move the decimal 2 places to the left. So that's what's going to be to the right of it. Remember, there's a total of 1. So what we're going to do is we're going to subtract the 0.1 from, so here's my calculator again. So I'm going to come in here and turn it on, and I'm going to get 1 minus 0.1075. Okay, so that's what I've got in my calculator. 1 minus 0.1075, because the 10.75% is to the right, and I always on my table want what is to the left. Okay, so here I've got my answer, and I enter, and I get 0.8925. So 0.8925 is going to be what I look up in the table. Okay, so here they're showing the picture. They're showing the 0.1075 to the right, and they're showing you that that's a 0.8925 to the left. Since our table is always going from the left to the right, then we're going to use the 0.8925, and we're going to go to our table. 0.8925 should be a positive z-score, so we're looking on the right-hand side, and there it is, and we're going to go to the left and up to get 1.24, which is, again, positive and greater than 0. All right, so now we're going to find the z-score that corresponds to P5 or percentile 5. Okay, so percentile 5 means that 0.05 is to the left. Remember, our percentiles are going to increase as we get up here to 100%, and our halfway mark will be P50. So P5 is 5%, and we're shading that little area to show what we mean. And the z-score that corresponds to P5 is the same z-score that corresponds to area 0.05. Okay, so the areas closest to 0.05 in the table are 0.0495 and 0.0505. So basically we have one of them that is 5, let's see, what is that? Tenths, hundredths, thousandths, 10,000ths. 5 10,000ths too low and 5 10,000ths too high. So what we're going to do is we're going to go halfway in between the two of them to get the answer. Now, if you're using technology, you don't have to worry about that. We only have to do that when we're using the table so that we can get as close to the exact value as we can. Technology is just going to be more accurate than the table is. Okay, So when we have a z-score and we're trying to go backwards to an x-score, I already showed you how we got this formula. Okay, so once we get that z-score, then we can go to the x-score. A veterinarian records the weights of cats treated at a clinic. The weights are normally distributed with a mean of 9 pounds and a standard deviation of 2 pounds. Find the weights x corresponding to z-scores of 1.96, negative 0.44, and 0. Okay, now the 1.96 is to the right of the mean, and the negative 0.44 is to the left of the mean, and the 0 z-score is exactly the mean. So the 0 should be right at 9, shouldn't it? But we're going to use the formula on each one of these. So there's the formula. We plug in the z-score of 1.96 right there where the sigma is, okay? And the sigma was 2 and the z-score was 1.96. And then we end up getting 12.92 pounds, which is bigger than the 9-pound mean. The second one should be lower because it's to the left, and it's 8.12, which is lower than the 9-point mean. The last one should be exactly equal to the mean, and it is. Okay, so now let's look at another one. Finding a specific data value. Scores for the California Peace Officer Standards and Training Test are normally distributed with a mean of 50 and a standard deviation of 10. An agency will only hire applicants with scores in the top 10%. So when we're doing a little curve here, we're talking about the 10% that's on the right, aren't we? What is the lowest score you can earn and still be eligible to be hired by the agency? So aren't we looking for the 90th percentile? The top 10% is going to be the 90th percentile, or P90, okay? So an exam score in the top 10% in any score is any score above the 90th percentile. Find the z-score that corresponds to a cumulative area of 0.9. So here's the picture of what we're looking at, and we're going to go, okay, this on the left is the 90th percentile, okay, and I can do this with my table or with technology, okay. So they're showing the 10% here, and they went and used the standard normal table, so they're using the 90% over this way, but they said the area closest to 0.9 was 0.8997. Okay, so the z-score that corresponds to that area is 1.28. So the table, you just can't be quite as exact as you can with the technology, which I'm going to show you in just a minute. Okay, and then we take the, oh, this is a different problem. I'm going to go ahead and show you that technology for this one right now so that we don't have to always use the table here. Okay, so we're back on this one. We're going to do this one with technology. We were talking about the 10% to the right, which meant the 90% to the left. When we went to the next slide, they had to estimate with the table because they could not do a 0.9. What we're going to do is use the calculator, and notice what I've done here. I've used an inverse normal, which I'll show you how to get there in just a moment. And then I'm putting the area, which was 0.90, and then I'm going to put the 0, which was the mean because it's already standardized, and 1, which was the standard deviation because it's standardized. So on the technology, I'm able to use the 0.90, and then the mean and the standard deviation is all that this one takes. And I end up getting 1.28155, and they got 1.28 from their approximation of the table. So that was pretty good. Okay, ours was more exact. To find that inverse normal, you're going to go to a second distribution here. You're going to go down right below our normal CDF, and you're going to get the inverse normal there. And then just hit enter, and then put in your 0.90 there, 0.90, because that was our area under the curve. And then we're, oops, I should not have put that parenthesis. We're going to put a comma, and then a 0, and then a comma, and then a 1, and then we're going to close our parenthesis, and we get the 1.28. 1. So hopefully that is helpful to you. And we got a little bit more accurate answer than they did. Okay, so now once we have found here the 1.28 is what they're using, so we'll just continue with what they have. They go to the next one. They say, okay, now I want an x value. The 1.28 is a z-score. So I'm going to put my 1.28 right there where the z is, and I have a 10 for my sigma. Okay, so now they're going back to the 10 for the standard deviation and the 50 for the mean. Okay, so the original test scores had been normalized, so that's why we used the 0 and the 1, because they had already been normalized when we got the z-score. So, but the test score was 50, and the x value that's going to go with that is going to end up being 62.8. So the lowest score you can earn and still be eligible to be hired by the agency is about 63. Okay, so if you want to go into, what was that? The California Peace Officer Corps. Okay, so this one is an example from your book. Okay, when designing equipment, one common criteria is to use a design that accommodates 95% of the population. We have seen that only 46% of women satisfy the height requirements for U.S. Air Force pilot. What would be the maximum acceptable height of a woman if the requirements were changed to allow the shortest 95% of women to be pilots? That is, find the 95th percentile of heights of women. Assume that the heights of women are normally distributed with a mean of 63.7 inches and a standard deviation of 2.9 inches. In addition to the maximum allowable height, should there also be a minimum required height, and why? Okay, so they've given us a mean is 63.7 and a standard deviation is 2.9. So we're going to put our mean and our standard deviation on our board. All right, so notice that they're drawing the picture first. They have the picture shows the normal distribution with the height x that we want to identify. The shaded area represents the shortest 95% of all the women. Okay, and so our mean was 63.4. Our standard deviation is 2.9, which I have on the board. And we're looking for what is the x value that is going to go with the z-score here. Now, where did they get this z-score? I'm going to show you in just a minute. All right, so we are on the positive side of our z-score chart. If we go on down here, we're looking for a 95th percentile. So look at this right here. We've got 0.9495, and on the other side we have 0.9505. So 95% is exactly right halfway in between those. This one is 5 10,000ths low, and this one is 5 10,000ths high. So halfway in between is going to be the z-score that we're looking for. So we go to the left, we get 1.6, and then we're going to go up and we're going to get 4. And then since we're right in between them, we're going to say, oops, you can't see that, can you? Let's see. Try to move that so I can point at the same time. So we had this one is going up. See this line going up here is right halfway in between. So it's going to be 0, 4, 5 because it's halfway in between those. So it's going to be the 1.6 on this side and then 45. 1.645 should be the correct answer. All right, so over here for the z-score, they put 1.645, and they have the mean was 63.7. Once we're talking about a z-score, we're talking about the standardized normal table. So the mean is 0, and the z-score we're looking for is 1.645. We need to find the x value by using that formula that they gave us before. And we're going to do it with the formula first. So here's my little table. Okay, so we're going to go, we already found the p the 0.95. So what we're doing now is z-score is 1.645, and we're transferring that to an x value. So now that we're doing from the z-score to the x value, we're going to have to use the mean of the distribution, not the 0 and the 1, because we're going from standard values to the regular. So we're going to use x equals mean plus sigma z, or z sigma. It doesn't really matter which way we write it. So the mean is going to be our 63.7, which we'll put right there. And our sigma is going to be our 2.9. And our z-score is going to be our 1.645. And now we're going to plug that into a calculator and come up with the answer. So here we go. All right, so here is our calculation. I'm taking this formula that we just figured out. I'm taking 2.9 times 1.645, which I did there. And then I added it to the 63.7, which I did right there. And we get 68.4705. Okay, and that was done with the table and a calculator, 68.47. And now we're going to look at how they're doing it using the technology. They're using here an inverse normal to go back to the x value. So technology will provide the value of x. So since we have the x value here, we're going to get the x when we put in the probability that we want. So let's go do the same thing using our inverse normal table. Okay, so we wanted to do our 0.95, so we're going to go second distribution. We're going to go down to inverse normal because we're trying to get out our x. Okay, so we're going to put in our 0.95, which was what the parameters were. We're going to put in our mean, which is 63.7, and our standard deviation, which is 2.9. And we're going to enter, and we're going to get the 68.47 that we just got using the other method. And there they are doing it using the Excel inverse normal. Okay, so here they're doing the same problem again using the table. We already did that, so I'll just let you look at the screens. Okay, they got the 1.645 using the table the same way we did. Okay, that halfway in between the two. 0.95 is one that we use a lot. So that's one that you're pretty much going to memorize. 1.645 is 95%. That's a z-score that you're going to see. In fact, it's used so often that we have little tables down at the bottom of the page that you can see that has the 95th percentile in it. And then we're going to do the same thing. Again, they're doing the same problem, but they're doing it with the value here. So we're going back to getting the 68.47 again. And 68.5 inches is reasonable because it is greater than the mean of 63.7. So basically 68.47, they're just rounding it to 68.5, which is a reasonable parameter to use. Okay, so a requirement of a height less than 68.5 inches would allow 95% of women to be eligible as U.S. Air Force pilots. There should be a minimum height requirement so that a pilot can easily reach all the controls. That would be dangerous if the pilot could not reach the controls. Okay, so now let's talk about what is a critical value. For the standard normal distribution, a critical value is a z-score on the borderline, which is separating those z-scores that are significantly low or significantly high. Okay, and we've talked about kind of a thumb rule that 2 standard deviations to the right and 2 standard deviations to the left might be those critical values, but we've talked about also that that's not a hard and fast rule. Okay, the expression Z alpha, this is a little alpha over here. The Z alpha denotes the Z-score with an area of alpha to its right. I had to plug in my phone. Okay, so it says find the value of Z 0.025. Let alpha be 0.025 in the expression Z alpha. Okay, now they will give you the parameters for what is a critical value. Sometimes they will just say to use the default critical values, but they're free to tell you what the critical value is. All right, so basically we're looking for 0.025 being that boundary there. So here we've got the area here being 0.025 and the area over here being 0.025. And that's a common one because guess what's going to happen if we take 95%, and remember 95% of all the data is in left boundary -2 Z-score to right boundary 2 Z-score, and then we take the 95% and we subtract that from 1 and we've got 5%, which means that in each tail we would only have 2.5%, and that's what they're indicating right here. Okay, so let's read this. The notation Z 0.025 is used to represent the Z-score with an area of 0.025 to its right. Okay, refer to the figure and note that the value Z is 1.96. Remember, you could find that from your chart, your table, or you could find it from your standard normal, and then refer to the figure and note that the value of Z is 1.96, has an area of 0.025 to its right. So the Z-score is 1.96 that goes with the area of 0.025. So the 0.025 is the area to the right, and the Z-score is 1.96. Note that Z 0.025 corresponds to a cumulative left area of 0.95975. Okay, so how do you tell that the 0.025 is to the right instead of to the left? Okay, so we need to look at this because this would be an important distinction. We've got the area over here is 0.025. The area on this side is 0.025. This score, Z-score, is -1.96. This Z-score is +1.96. Okay, so if we're looking for the one to the right, we're going to get 1.96. If we're looking for the one to the left, we're going to get -1.96. Okay, so it says to find this Z-score, locate the cumulative area to the left. In other words, locate 0.975 in the body of the table, or use your technology. All right, so when finding a value of Z alpha for a particular value of alpha, note that alpha is the area to the right of Z alpha. So basically they're defining this one. The area here is the area to the right. But table A2 and some technologies give cumulative areas to the left of a given Z-score. Okay, define the value of Z alpha. Resolve that conflict by using 1 minus alpha to get the value that you need to use for your table. For example, to find Z 0.1, then we're going to say, well, the 1 minus 0.1 is going to be 0.9. So we would use the area as 0.9 to the left. So they're defining this as always being to the right. And we are done. Here is your homework for 6.1. And don't forget to do your My Math Lab homework, which should be up and available to you before I go to bed tonight. And then here is your 6.2. And also remember, there's not much of 6.2. Just make sure that you are familiar with these exercises. And we have thoroughly covered 6.1 and 6.2. And I hope these videos will help you. This is Mrs. A, and may God bless your day.